So let's try to understand what is the Newton-Raphson method and how it can be used for solving an optimization problem. Typically, a Newton-Raphson method in engineering is used for root finding algorithms. And if you have taken numerical math or numerical applied math courses, in that sometimes you have problems of interest in which you are interested in finding the root of an equation, and that's where the Newton-Raphson method is being used. Now, what has been done in the optimization domain is that approach of root finding has been modified and used to also solve for the optimization problem. So let's try to understand the connection between root finding and optimization problem, and then that will help us in basically developing an algorithm that will be based upon the Newton-Raphson method that we will be using. Okay. So, I want to start with, function expansion. You can expand a function around a point xk using this series, right? And this is where this is the Newton series that is typically used, right? Where you significantly have higher order terms, and this sort of expansion could be written, right? Now, from this expansion, from this series, if you neglect the higher order terms from this terms onward, right, you can use this remaining function. And if you say that these higher order terms are not contributing significantly, then you can use this equation to solve for equation numerically and find the root of an equation numerically. Okay, so let's focus on that problem. So when I'm talking about finding an equation, root of an equation, let's say we have a function. So this is a function axis, and let's say we have essentially this is an x, and since we are talking about one variable problem, we have these two axes of x, and let's say the function is highlighted by this yellow curve that is out there, right? So what is the root finding problem? What we are interested in root finding problem is where this function value is equal to 0. So the root finding problems typically is finding problem where we only are interested in finding all the values of x where this fx is equal to 0. So if in the diagram, I think what we are really interested in, if this is the function, then we are interested in locating this point, right? The point which is here, and this point which is point right here. This is where the function fx is touching the x-axis, or in other words, where the function fx is equal to 0. So we are essentially interested in locating these 2 points, and that will essentially fall in a root finding point. And the Newton-Raphson method is basically used for finding the roots. Okay, so how do we do it, right? Again, we know that at this location the function value is going to be equal to 0, so we can substitute this 0 here at fx equal to 0, and we can take this right hand side and expand it and use this to create a numerical scheme which can be used to solve for root finding problems. So let's carry on and let's do that. So if I substitute this 0 here, this equation, and neglect the higher order terms, then this whole equation could be written here. And again, why we substituted 0? Because we are interested in root finding or finding fx equal to 0. So that's why we did it. Now you can see this is x minus xk term, right? This x is now indexed because this is something that we are interested in finding. This x is indexed xk plus 1, and that basically xk plus 1, and that basically is used to find out the next iterative solution where we should be moving, and that's what we will be doing. So this essentially we will be substituting here xk plus 1. Okay, and again, this is a revision of a numerical method that you might have learned in your bachelor's or undergraduate studies, right? So if we do that, from there we can basically rewrite the equation that is given on the top. So if I erase this portion, right, equation that is going on the top, and we have xk equal to xk minus fx by f dash x, right? So what we did is we substituted xk, and now once we do that, right, I can take this terms and reorganize the term to find this xk value. Now this becomes an iterative scheme where I start with some initial value xk, and then in iterative fashion I iterate using the equation here, and I can use this to solve for the root finding problem. Okay, but the focus of our lecture is not root finding. The focus of our lecture or our course is on optimization or finding out the minimal value of the function. So if I take the same function right here, the function that we are discussing right here, right, the function that we have, let me, again quickly draw fx, this one, and then we have, this one. So for this function, as I said, the root finding are these 2 points, but if we are interested in finding the minimal value, which is the optimal problem of this function, then we are interested in locating this point, and this is where, the function has the minimum value or the lowest value among all the locations that we are showing here. So we are not interested in finding this 2 locations, but we are interested in finding this, which is an important problem in optimization. So our focus of the course is slightly different than the root finding, and it is more focused on finding the location of the optimal point or the minimal value of the function that is there. So in that case, we will be actually interested in finding the location of this point, right here. Okay, so let's see how can we modify a root finding equation and convert that into basically a scheme or iterative scheme to find the minimal value. So I will take the same algorithm that is used to find these 2 points and convert that algorithm to find this point, and that's the basic interesting part of what I'm going to talk about. So what we can do is, if you look into these equations that we have here, right, if this is the equation, what I can do is I can take a derivative of this equation, right, and I will just do that for and I will explain why we are doing. I take a derivative of this function. If I take a derivative of this function and neglect this higher order terms, then this will be, we will take a derivative of this function, and then we will take a double derivative of this function, right? Okay, and keep this in mind. If I take a derivative of this, we will have a single derivative here, we will have a double derivative here, and we will use this information in the next slide. So let's move on to the next slide and see how can we use a Newton-Raphson method, which is used for root finding, to find a solution of the optimization problem. Okay, so again, this is something that I wrote in the previous slide, and I'm bringing here. I took the differentiation of the function that was there, and this is what I have. I am obviously neglecting the higher order terms, so there are plus higher order terms here, right? So this is higher order terms, and I'm basically neglecting and cutting out those higher order terms that is out there. Okay, so let's get into some intuitive understanding of how I can take a Newton-Raphson method and convert that into optimization problem. So again, as I mentioned, we are interested in basically finding this point, which is the optimal point, and that's of interest in optimization. But in root finding, these 2 locations are interested. Now, one of the things I want you to notice is what happens to the function here. Okay, if we have a function which has a minima here, right? Right here, if I let me precisely draw this because it's important concept. So if you have this function right here, right, and this is the location of the optimal point, here the derivative of the function is going to be equal to 0, right? It will be flat, it will not be inclined, right? So the derivative is going to be equal to 0, and that is the information that we are going to use. Okay, so what we are going to do is we can take a problem which is fx equal to 0, that's a root finding problem. But now what we can do is I can take that function and take a derivative of that function, and then when I find the root of the derivative of that function, I will be essentially forced to find this optimal location, right? And that is what concept that we are going to use to find and convert an algorithm of an optimization problem, right? So if you have this function, right, maybe, and I'm just for the sake of showing it, I don't know exactly what is the nature. So illustrative way, if I take this function, maybe I will have another function, right, which will be something like this. Okay, and this function, let's call this function as the derivative of the original function in the yellow line. And if I find the root of this function, right, here is the root of this function, here is where fx is equal to 0. Okay, I'm essentially finding out the problem or location of the optimal solution in the original function fx. And this is the connection between root finding and optimization problem. So in the root finding, what we are doing is basically we are converting an optimization problem as a root finding problem, but instead of taking fx, we are finding the root of f dash x, or first derivative of the x itself. And this is why I wrote this equation here, because what we have done is when we have converted this problem of finding the root of f dash x, right? And that's why I took the derivative. Now what I will do is I will substitute this equal to 0, and that will give me an iterative scheme to find the location of this point rather than this point. So let's carry on and write those equations that we have here. Okay, and then it will repeat one more time. This problem is finding fx equal to 0, but when I convert that problem f dash x equal to 0 and find the root of f dash x, that will be in the original function space, that will be equivalent to finding this point. Okay, and that's the main concept, and that's the main connection. So we again f dash x equal to 0, and from here again, similar to what we have discussed in the previous slide, we will write this equation. But the equations, as you note, will be slightly different. Here the xk plus 1 is equal to xk minus f dash xk divided by f double dash xk, or the second derivative of xk. And this you will see in the previous, when the root finding for the original function is, this portion of the equation is essentially different. So this is the iterative scheme or the algorithm that we are going to use to find the solution of an optimization problem. So let's take a very specific example and go through an iterative steps to see how we can use this equation to find the solution of an optimization problem.